we're going to take some time and go over the solutions to the practice problems that you just gave a try to. All right, let's look at number one. Number one said the square root of 4,356 is an integer. Without a calculator, determine what that integer is by eliminating possibility. And then you're asked to do the same for 8,464. So if we didn't have a calculator, we would first need to come up with a systematic list of possibilities, and we'd want to use some number sense to help us create a short list and figure out what possibilities emerge in that short list. So in terms of number sense, we need to be thinking in terms of perfect squares. What does this number, this 4,356, what two numbers squared, and I tend to go with benchmark numbers of 10, what two benchmark numbers, once squared, does it lie between? And if you think in terms of 60 and 70, 60 squared is 3,600, and 70 squared is 4,900. So it has to lie somewhere between those two numbers. And quite frankly, it's pretty well near in the middle. So that's going to be able to that gives us some information to help us determine exactly where it's going to lie between those. In addition to using that aspect of number sense, we want to look at the last digit. Since that last digit of 4,356 is a 6, we need to think of a number between 60 and 70. We know it's got to be close to the middle because we talked about the fact that it lies exactly almost between 70 squared and 60 squared. But we need a number between 60 and 70 such that when you multiply it by itself, the number in the ones place will produce a 6. So I wrote out the list of the numbers between 60 and 70. I have 61 to 69. And again, I mentioned this is probably going to lie somewhere in the middle. And if you did 64 times 64, that 4 times 4, which you multiply first, that's going to give you a 16, a 6 in the ones. The same with a 66. If you multiply 6 times 6, you get 36. So you'll have a 6 in the ones. Those are the only two numbers that do it, and they lie right around the middle. So it has to be one of those two. So you can eliminate those other possibilities, the 61 to 69. Go ahead and multiply those two out, and we see that 66 has to be the square root because we indeed get 4,356 when we square it. Okay. Let's look at number one, part B. Same strategy, but we're trying to find the square root of 8,464. We know that 90 squared is going to give us 8,100, and we know that 100 squared is going to give us 10,000. So we know that some number between 90 and 100 has to produce this 8,464. And quite frankly, it's going to have to be closer to the 90 end because it's much closer to 8,100 than it is to 10,000. So as we did with the previous one, we want to find a number or numbers between 90 and 100 whose ones digit, when multiplied by itself, would produce a 4. So I didn't draw out the whole list this time because you can start to use some of that number sense and strategic competence to just automatically eliminate in your head. And I know that 92, the 2's when multiplied will give me a 4, and that 98, the 8's when multiplied would give me a 64. Both are producing a 4 in that ones area. But since I know that this number has to be closer to 90 than it does to 100, I defaulted to just trying 92 squared first, and I indeed got 8,464. Okay, let's look at the solution to number 2. Squares with missing digits. It reads the 5-digit number it would be 5ABC9, which would be some 50,000 number, is the square of an integer where A, B, and C each represent a missing digit. If all 5 digits are different, what is the 5-digit number? So basically what we're looking for is the square root of this number. And again, we need to come up with a list and then eliminate. So the first thing that I would do is try to determine what two whole numbers, when squared, would produce some type of number that what we're looking for lies between. So I know if I squared 200, I'm going to get 40,000. And if I move upwards to the next benchmark number and I square 300, I'm going to get a 90,000. So I'm looking at some number between 200 and 300. That's a lot of numbers. We don't want to try all of those. No, our number is going to lie closer toward 200 than to 300 because it's in the 50,000s, right? But we can write then that that first digit would have to be a 2. The next number that we could really figure out pretty quickly is the last one because we need a digit such that when you multiply it by itself, it's going to give you a 9. Well, that digit would be a 3. So we know the first digit has to be a 2, the last one has to be a 3. The remaining numbers could be any of the numbers between 1 and 9. But it's likely that it's going to be small since 300 squared gives us that 90,000 and our number is in the 50,000s. So I tried 2 first. So when I put a 2 in, I had 223 times 223 and I got 49,729 and that was too small. So then I tried 3 and I did 233 times 233 and that indeed gave me 54,289. The A, the B, and the C were all different, which is what the criterion the problem said. A would be 4, the B would be 2, and the C would be 8. And that's the solution to number 2. Okay, number 5, eggs in a basket. It says if the eggs in a basket are removed 2 at a time, 1 egg will remain. If the eggs are removed 3 at a time, 2 eggs will remain. If the eggs are removed 4, 5, or 6 at a time, then 3, 4, and 5 eggs will remain respectively. What if they are taken out 7 at a time? No eggs will be left over. Find the least number of eggs that could be in the basket. Okay, so the one thing that we do know is that the number of eggs in the basket is divisible by 7. So I made a pretty big list of the multiples of 7, and you see that I did that from the number 7 to 226, and I just decided arbitrarily to stop there and hope that my number is somewhere in between there. Of course, if I realize through eliminating that it's not, then I would have to go on, but I'm going to hope for the best. We do know that this number is not divisible by 2, 3, 4, 5, or 6 because when you divide by that, you get remainders. So we can take that list of 7 and or multiples of 7, and we can take out any of the numbers that are divisible by 2, 3, 4, 5, or 6. And you see then that I get rid of 7. Now you're probably thinking, why are you getting rid of 7? That's not divisible by any of those. That number is too small to fit the criteria of producing those remainders when divided by 4, 5, and 6. So that's why that one is out. But the rest are either divisible by 2, 3, 4, 5, or 6. The ones that are in squares are not. They're divisible by 7, and they are not divisible by 2, 3, 4, 5, or 6. That leaves me with 4 choices, 49, 77, 91, 119. What I need to do is now test these and divide by 2 to see if I get a remainder of 1, by 3, remainder of 2, by 4, remainder of 3, and so forth. I start out with 49, and as soon as I divide by 3, I get a remainder of 1 instead of 2, so that's a no. I try 77. When I divide it by 4, instead of getting a remainder of 3, I get a remainder of 1, so that's a no. When I tried 91, I divided by 3, and I got a remainder of 1 instead of a remainder of 2, so that's a no. Finally, when I try 119, all the criterion fit. When I divide by 2, I get 59 remainder 1. When I divide by 3, I get 39 remainder 2. When I divide by 4, I get 29 remainder 3. When I divide by 5, I get 23 remainder 4. And when I divide by 6, I get 19 remainder 5. So 119 it is. Our last problem is a cryptorhythm. It is Nelson plus Carson equals reward. And it reads as follows. A story from the Old West tells the tale of 2 famous outlaws named Carson and Nelson. The wanted poster calling for their arrest indicated that a substantial reward would be offered to the person who caught up to both of them and brought them in for trial. Amazingly, it turned out that the poster contained a great cryptorhythm. All who saw the poster realized this and spent their time solving the puzzle rather than looking for Nelson and Carson. When Nelson and Carson heard all the ruckus about the poster, they also tried to solve the problem. However, they weren't too bright and ended up visiting their local sheriff for a clue. He told them that n equals 5, and then he arrested them. They solved the problem during the time they spent in jail. Each letter in the cryptorhythm stands for a different digit. Find the digits that the other letters represent. Okay, so what I have on the screen just shows you the order in which I deduce what each letter represents. And we obviously are given that n equals 5. So that's my very first step, and we see that on the right. And I put my digits 0 through 9 out, and underneath them, I then would indicate, as it would happen, what each of these letters represent. So you'll see here that I put in that n is 5. Now, the next thing that I know is that D has to equal 0. Well, how do I officially know that? Because n plus n, which is 5 plus 5, that's 10. So that's going to give me a 0, and I'm going to be carrying a 1. The next thing that I know is that R is odd. And I also know that A is likely 9. Now, let's talk about how I know first that R is odd. Well, I've carried a 1, and you're adding the same two letters here. So whether those same two letters are odds or they're evens, when you add the same two numbers, you always get an even, but then you're adding a 1 to it. So R has to be odd. So I wrote that down. But then as I'm looking through and I see where else R is situated, and I'm looking at my 9, as well, I realized that 9 likely has to be, or A has to be 9, because over here you have E plus A equals E. Now, you've already exhausted and used your 0. So A cannot be a 0, but you're going to need a very high number to produce a 2-digit number such that this number down here is exactly the same as that number up here. This is telling me, hey, you're going to be carrying a 1 to produce like a 10 here so that you can get a mirror image of this number here and here. So I'm going to let 9 represent my A. And if I do that, and I know that R is odd, I'm going to place R as 7 because the other values are going to be too low. How do I know that? Well, I've got to get R here, and I already know that N is 5. So we know it's odd. I've used 9, so it just by process of elimination gives me a 7 for my R. So I now have a series of digits, which is good. If I know that R has to be 7, and I also know that I'm going to be carrying a 1 because I needed to produce a 2-digit number to get a mirror image of the E's here. I have a 1 plus a 5. I know it's got to produce a 7, so I know that C would have to be 1. Okay, what about O? It says on here that O has to be a high even. Why would it have to be a high even? Well, I know that A has to be 9, and I'm adding the same two numbers here. So I need to produce an odd, meaning I'm going to need to carry 1. So I need to put 2 digits here that will allow me to carry 1. So I let O equal 8. When I let O equal 8, I automatically know that my S's are going to need to be 4 here because I need to produce a 9, and those are the only two numbers that will allow me to do that. L and R, which is left in this column, have to be, must be 2 digits that produce a carry of 1 because I know that I need this carry of 1 up here. So I just go ahead and I try and I let L equal 6 because I already knew that R had to be 7. When that happens, that automatically makes W a 3, and that gives me that carry of 1. And I know that if I carry that 1 up here and I have a 9 here, that if I put a 2 in for E, that will produce a 12 when added all together, and that allows that mirror image then to occur. And that's how I deduced what each and every one of these letters would have to represent in terms of their numbers. So we get that A is 9, O is 8, R is 7, L is 6, N is 5, S is 4, E is 2, C is 1, and O is 0.